Chapter 18 and the remainder of this unit starts to focus on sampling distribution models. When we gather data from a population, it's very difficult to gather data from the entire population, so we take samples. Well, each person can take a different sample. Each sample still represents the population, but each sample will have slightly different data in them, which will also create different standard deviations and different averages. So what this chapter is about is looking at what happens when we take into account every possible sample there is. What does the overall data look like? So let's take a look at some important information. So to get answers to categorical survey questions, which, if you remember, categorical is questions like, what's your favorite color? Things that fall into a category. We always randomly select a sample from the population and we ask them our question. The results we get from that sample we call a sample proportion. And it's denoted, and you guys have seen this notation, by p hat. The hat, if you remember, we used it before to mean approximation. Because this data is coming from a sample, it is an approximation. So P simply stands for proportion, and the hat means that it came from a sample. The results from the entire population, which we aren't able to gather, but we do have letters to represent them, it's denoted by P. So P means proportion. If it's just P, it represents the whole population. If it's P hat, it represents the sample. So if we choose a new sample from that same population, we are going to get, as I said, a slightly different sample proportion. So that P hat might be different than our first P hat, simply because we're surveying different people. In this chapter, we are focusing on the variability, in other words, the differences that come with choosing different samples every time. So this is just some general information to think about. Suppose that 45% of all adults believe in ghosts. Then what we would say is, because this is of all adults, we would say that P is 45%. Notice I said P, that means that it represents the whole population because it says 45% of all adults. We have simulated 2,000 different independent samples of 808 adults. So we went through and we took the entire population and we gathered samples of 808 people. And we did this 2,000 different times with 2,000 different samples. And we asked them the same question. The results for each P hat, so the results for each and every sample, are shown in this graph. So each sample, along the bottom are our proportions. These are our P hats. They are in decimal form. So our original P was 45%. That's this right here. That's for the population. As you can see, it's in the middle of the graph and it's basically the highest bar. But that was for the whole population. Each of these represents P hats. So like this bar right here, that is about 0.41, 0.42, and it comes over to about here. 50 is this mark up here, so there might be 10 samples that ended up with that mean. This bar right here, that's about 0.43. Well, it fell about right there. So about 60 of those samples had a mean of 0.43. So each sample, some of them had the same results, some of them had different. What do you notice about the shape of this graph? This should be a shape that you are familiar with. Hopefully you're starting to think, well, this is kind of that curve that we've seen before with the z-scores, and you're absolutely right. This looks like the normal model. You should notice that it is somewhat symmetrical. Is it perfect? No, but it is definitely symmetrical. It is unimodal. It has one mode in the middle, and the mean looks to be about 0.45, which was the percentage for the population. So it's not a coincidence that this is occurring. This is because we did lots and lots and lots of samples. So here are some important properties. If you take as many possible samples as you can, and you analyze each one and you get data about each one, what you're going to end up with is a histogram, like this one. This shows the simulation of what we would get if we could actually see every single proportion of all of the possible samples. This is a simulation. As we mentioned, this is definitely Udimodal. It's symmetric. The center of it is the P, again, the P from the population, because there's no hat. And more importantly, it looks like the normal model, because this is going to allow us to do some evaluating upon whether samples are good or whether samples are bad, because we're able to use z-scores in our blue sheet. So to use our normal model, we need some information. So the first thing we need is to know the mean. The mean of your histogram will always be your P in decimal form. Okay, make a little note here if you need to. Decimal form. The standard deviation of your proportion is the following equation. The square root of P times Q divided by N. Some notes, obviously, P we already know. This is the population. To find Q, we simply take 1 minus P, and N is our sample size. And so you'll type all of that in a calculator and you'll get your answer. So there are some required assumptions in order to be able to use z-scores and all of that. The first assumption is what we call the independence assumption. Every single sample must be independent of the other samples. In other words, they simply can't influence each other. That's a big assumption that we are able to make. The other assumption we have to make is that your sample size, it's your sample size assumption. Your sample size, which is your N value, must be what we call large enough, but it also can't be too large. So how do we know we can make these assumptions? Well, that comes with checking 3 conditions. So here's your conditions that you have to check before you proceed with your problem. First assumption you have to make is the randomization condition. Every sample must be truly random and not biased. That's an easy assumption that we're going to make. The 10% condition. This is the important thing. This is about the sample size. Your sample size can be no larger than 10% of the population. So if your sample size has 500 in it, the 500 is 10% of the population. So all we simply do is we tack a 0 onto that sample size. And so if your sample is 500, your population must be at least 5,000. And so when we get to the individual problems, we're going to discuss this as we go. Then also the success failure condition, which we saw in chapter 17, NP and NQ must be greater than or equal to 10. Again, we've seen that before. That was from chapter 17. We're just continuing that same assumption. So I'm going to work through some problems with you so you can see how we easily use a lot of the same skills that we've learned in our other chapters. So the candy company claims that 10% of the M&Ms it produces are green. In a really large bag of M&Ms, students found 500 candies and 12% of them were green. Is this an unusually large proportion of green M&Ms? So we're going to write down everything we know, and then we're going to start by checking our conditions. So the first number it gave us was 10%. I'm going to start off by writing that as a decimal. That will be 0.10. Now this is what the candy company claims is true about all of their M&Ms. So this is going to be your population number. We then know that in one bag of M&Ms, so there's a sample, students found 500 candies. So there's your sample size. Your N is 500 pieces of candy. And 12% of them were green. So this is data from the sample, which means that is your P hat, 0.12. So there's all of our important data. Now the first thing we're going to do is we're going to check our conditions. So the first condition we're going to check is the random condition. Well, how did the bit candies get in a bag? A machine. Do machines have any control over what they're doing? No. So we can definitely assume that this is random because a machine filled the bag. Next thing we need to check, the 10% condition. So our sample was 500. So I told you, tack a 0 onto that. And the question is it safe to assume that there is at least 5,000 M&Ms in the world? I would say it's very easy to assume that there is at least 5,000 M&Ms. Then the last thing we need to do is we need to check our NP and our NQ. So we're going to take 500 times 10% and 500 times, well, our other percent would be what's left, and 100 take away 10 is 90. So 500 times 10%, I end up with 50. And 500 times 0.90, I end up with 450. And those both have to be bigger than 10. So we've taken care of our conditions. We are good to continue. So now we need to come up with the rest of our info. Well, we know our mean. Our mean is our p-value. So I'll also write up here that this is our mean. But we also need to find our standard deviation. Well, that's a very easy formula to use. It is P times Q divided by N. So square root. P, we already know is 0.10, times Q is the remaining, so that would be 90, divided by how big is our sample? It was 500. So type that in the calculator, and in general, I round to 2 or 3 decimals. It depends. Like this one comes out to be very tiny. If you notice, it starts off with 0.0. So I want 2 non-zero digits. Let's leave it at that. So since the 0 is the first digit, I want 2 more. So 0.013. So there's your standard deviation. So now what we're able to do is we're able to find our z-score. So our z-score is going to be found by taking our x value. Well, it's not really an x value anymore because these are means, but because there was 12% in the sample, 0.12 is your x value minus your mean, which was 0.10, divided by your standard deviation, which is 0.013. So go ahead and type that in your calculator. Remember, z-scores, we always round to 2 decimals. And I get 1.54. Well, the question is simply asking, is this an unusually large amount? Well, here's the nice thing. We don't have to use our blue sheet for this. We talked about this, and it's been a long time. There was a cutoff for z-scores that made them unusual. And this was a general rule, and we'll jot it down again. I'll jot it down off to the side here. To be unusual, it has to be more than 2 standard deviations away. So if you look at this guy right here, that guy is not more than 2. So what we would simply say is, no, it's within 2 standard deviations. So let's take a look at the next example. So after hearing of the national result that 44% of students engage in binge drinking, that represents 5 drinks at a sitting for men and 4 for women, A professor surveyed a random sample of 244 students at his college and found that 96 of them admitted to binge drinking in the past week. Should he be surprised at this result? So let's write down again what we know. So the national result, which would represent your population, is 44%. So P is 0.44. The professor sampled 244 students. Now, to find P hat, we have to do just a little bit of work because it doesn't give us a percentage. It gives us a number. It said 96 out of those 244 students admitted to binge drinking. So if you take 96 divided by 244, you should get 0.39 for your P hat. So now that we've listed all of our important data, let's go through our conditions. So random. Well, this one's easy because notice right here it says he surveyed a random sample. Done. It says so, don't even gotta talk about it. 10% condition. So how many are in his sample? 244. I told you guys tack on a 0. Is there at least, you think, 2,440 students at the college? I would say it's safe to assume that most colleges have 2,440 students at them. So now we got to check NP and NQ. So we got to take 244 times 0.44, and we have to take 244 times, if you take 100 and take away 44%, you get 0.56%. And so for NP, I get 107, and for NQ, I get 136. So those are definitely no problem. So what's the next thing we have to find? Well, the next thing we need is the standard deviation. All right, so that was the big square root. It has P, which is 0.44, times Q, which is 0.56, divided by your sample size, which is 244. So if you type that in the calculator, and again I said I want two non-zero digits. This one starts off with 0.0, so the next two are 3 and 2. So then, now that we have our standard deviation, now we can find our z-score. So what was our proposed sample? 0.39 minus our mean, which was the original P, which was 0.44, divided by the standard deviation we just found of 0.032. Type that in the calculator, round to 2 decimals, I get negative 1.56. So is he surprised at this result? Remember, to be unusual, it has to be more than 2 away from the mean. So is this more than 2? No, it is not. So we would say no, it's within 2 standard deviations of the mean. And so that's example 2. So now let's take a look at example 3. So we're going to assume that 30% of students at a university wear contact lenses. We randomly pick 100 students. Let P hat represent the proportion of students in the sample who wear contacts. What's the appropriate model for the distribution of P hat? Specify the name of the distribution, the mean, and the standard deviation. Be sure to verify that the conditions are met. So this is basically going through and checking all of our conditions. So what do we know to start this problem? Well, we know that 30% of students at a university wear contact lenses. We're going to assume that that is P, so 0.30. And we randomly pick, so there's the N, 100 students. But we don't know any other numbers, so that's all we know right now. So let's check our conditions. Is this random? Does it mention random? Randomly pick. We're good. No need to talk about it. 10%. Well, our n's 1,000. I'm sorry, our n's 100. Add a 0. Do you think there's 1,000 students at a college? It is definitely safe to assume that. And what about NP and NQ? Well, N is 100, P is 0.30, N is still 100, Q is 0.70 because 30 and 70 make 100. So NP, I get 30, and NQ, I get 70. And those are both bigger than 10, so we're good. So since we've checked our conditions, that was this part right here, we are able to say that a normal model is our model. It also wanted us to state, let's see, specify the name, the mean. So we already know, our mean was already 0.30, but we needed to calculate our standard deviation. So square root 0.30 times 0.70 divided by 100. And remember, again, 2 non-zero digits, so I get 0.0, so the next 2 would be 4 and 6. So that is what the first part was asking. So now, what's the approximate probability? So now we finally have a probability question. This is where your blue sheet's going to come in handy. That more than, so that means we're shading to the right, 1/3 of this sample were contacts. So we just now were told our p hat. Our p hat is 1/3, or if you type that in the calculator, 0.33. So our z-score is going to be our p hat, which is 0.33, minus our p, which is 0.30, divided by our standard deviation of 0.046. Z-score, rounded to 2 decimals, I get 0.64. So that's like 0.64. So because this said probability, we actually need our picture. Zero's in the middle. 0.64 is over here. And we wanted it more than, so we want it to the right. So when you look it up on your blue sheet, we need to subtract. So if you look on your blue sheet and you go down to 0.6 and you go over to 4, I get 0.7389. But because the blue sheet only shades to the right, only shades to the left, we need to take 1 minus that answer to get the answer that we want. And so if you type that in your calculator, I end up with 0.2611. So that's our chances, or our probability, that more than 1/3 of this sample wear contact lenses. Right, so let's look at the next. Suppose that about 13% of the population is left-handed. A 200-seat school auditorium has been built with 15 lefty seats. In a class of 90 students, what's the probability that there will not be enough seats for the left-handed students? Check conditions first. Okay, so let's talk about what we know. We know 13% of the population is left-handed. So that's population, that's 0.13. Now, we have a class of 90 students. So there's our sample size. And now we got to think creatively. Our p hat, because we're trying to figure out what's the probability that there will not be enough seats for the left-handed students. So if there's not enough seats, that means that there has to be 16 lefties in the room. So our sample would be 16 out of 90. And if you type 16 out of 90 in your calculator, you should get 0.177. So we're going to round that up to 0.18. So I didn't use 15 because 15 would have been enough. But it said, what's the probability there will not be enough? So that means that there's 16 or more students in the class. Okay, so now we need to come down and we need to calculate we need to do our conditions. So first of all, random. Well, it doesn't say random in the problem, but it's probably safe to assume that because we're just using a class that we checked it randomly, we're going to make that assumption that it's fine. 10%. Our sample only had 90 people. Is there at least 900 students at a school? Yeah, I would say that's safe to assume as well. NP and NQ. So 90 times 0.13 and 90 times if you do 100, take away 13, I get 87. So 90 times 0.13, I get to be 11 students. And 90 times 0.87, I get 79. And so they're both over 10, but just barely. So what's the other thing that we needed? Well, we know our P, but we need our standard deviation. So our standard deviation, big square root, P, so 0.13, Q, 0.87, divided by N, which is 90. 2 non-zero digits, so 0.0, and then it ends up being 3, 5. So now we got to calculate our z-score because we're trying to find the probability. So what was our proposed sample? 0.18. What is our mean? 0.13. Standard deviation? 0.035. And so, again, type that in your calculator, rounding to 2 decimal places, and I get 1.43. So if we look at a pretty little sketch, so here's our normal model. Zeros in the middle, 1.43. Now, if you remember when we were up here doing p hat, we talked about there's 16 or more students. That's the only way that there would not be enough seats. So I'm going to shade to the right. So when I look up 1.43 and I get 0.9236, because again it's to the right, I need to take 1 minus that. And hopefully you end up with what I got, and that's 0.0764. So what's the probability that there will not be enough left-handed desks? Only that small probability. So let's look at our last example. A restaurateur anticipates serving about 180 people on a Friday. And believes that about 20% of the patrons will order the chef's steak special. How many of those meals should he plan on serving in order to be pretty sure of having enough steaks on hand to meet the customer demand? Justify your answer, including an explanation of what pretty sure means. So this one is a little different. We're going to work backwards. So let's figure out what we know. We know that 20% of all patrons will order the special. So that means that P is 0.20. He also anticipates about 180 people on Friday. So that's your sample size. We don't know anything about P hat yet. So we're going to come back to that. So let's go ahead and check our conditions. So our conditions First question, are we doing this randomly? We're going to go ahead and say yes. 10%. So 180 patrons on one night. Do you think that this restaurant sees 1,800 customers? Well, if they see 180 on one night, I would probably say it's safe to assume that they've seen that many customers in total. In P and NQ. So 180 times 0.20 and 180 times 0.80. So I end up with 36 for that one and 144 for that one. So far we've checked our conditions. Everything is good. What else do we need to know? Well, we already know our mean is 0.20, but let's go ahead and find our standard deviation. So 0.20 times 0.80 divided by 180. 2 digits that aren't 0, well, it just so happens that you end up with a 0 and then it rounds up to 30. So I'll accept that. Don't worry about another digit. So here's the problem. We have no clue what our sample is. We're trying to figure out how many steaks should he have to meet customer needs. Well, he wants to be, and there's a very key phrase here, pretty sure he has enough steak. Well, pretty sure, we want to be confident. So what we're going to do for the phrase pretty sure, we're going to say that that means within 2 standard deviations. So here's what we're going to do to find the number of steaks we need, because we don't need p hat to do that. We literally are going to do what it says right here. We want to be within 2 standard deviations of the mean. Well, what was the mean? It was 0.20. We want to have 2 standard deviations above that in steaks. So 1 standard deviation was 0.03. I'm going to add another because I need 2 standard deviations. So what we're going to assume is we need enough steaks for 0.26% of your people. So this is the percent of the total. In other words, this is kind of like our p hat now. We're going to guess that that's like our p hat. So I simply want to know, what is 26% of the sample? So there's 180 people coming tonight. If you multiply that by 0.26, you get 46.8 people will order steak. So you need 46 to 47 steaks to be pretty sure you have your group covered. And that's the end of your lesson.